problem demands millimeter precision across 13 acres of stone in 2550 BC? What threat required alignment to true north within a fraction of a degree before the compass existed? And why would a tomb demand tolerances rivaling modern engineering? Tonight, we are not asking how the Great Pyramid was built. We are asking something far more unsettling. Why was it built to tolerances it didn't need? We all know the Great Pyramid did not need to be this precise. Its base, carved directly into bedrock, is level to within roughly 2 centimeters across a span of 230 meters. 13 acres of stone, flattened with an error smaller than the height of your thumb. Its sides are aligned to true north within approximately 0.05 to 0.15 degrees, a fraction of a degree so slight that even modern surveyors pause in admiration. Its corners approach right angles with deviations measured in arc minutes. Its original white limestone casing stones were fitted with joints averaging around half a millimeter, in 2550 BC, before iron tools, before compasses, before precision optics, before modern mathematics as we know it. The pyramid is one of the most structurally stable shapes ever conceived. Gravity locks it into permanence. The wider the base, the more secure the mass. Even with visible asymmetry, even with centimeter-level irregularities, even with several degrees of misalignment, the structure would still stand. 4,500 years later, it would still stand. Engineering is never about perfection, it is about sufficiency. Bridges are built to tolerances they require, not beyond. Foundations are leveled within acceptable margins, not cosmic ones. Every added degree of precision costs exponentially more in labor, material, time, coordination, and risk. Precision is expensive. Civilizations do not pursue millimeters across 2.3 million stone blocks by accident. Which brings us to the question that begins our journey. What problem demands this level of accuracy in 2550 BC? Was it structural necessity? No. Was it durability? Perhaps, but a pyramid's very geometry already ensures extraordinary longevity. Was it theology? The pharaoh expected to become a god. The structure had to align with the cardinal points, north, south, east, west, perhaps to guide his soul toward the imperishable circumpolar stars. In that cosmology, alignment was not decorative, it was directional. Was it political? A national project involving 20 to 30,000 skilled workers. Limestone quarried locally, granite beams weighing up to 80 tons transported from Aswan, casing stones ferried across the Nile from Tura, bread, beer, medical care, administrative records. This was not slave chaos, it was organized supremacy, precision as demonstration of power. Was it engineering competition? A divine rivalry in stone? A desire to build not merely large, but perfect? Or was it something more unsettling? Some researchers have suggested that the pyramid may have functioned not only as a tomb, but as a calibrated monument, a structure embedded with astronomical, geometric, even geodetic intent, a reference aligned to Earth itself, a fixed point against which the heavens could be measured. We will examine every one of these explanations. The divine machine, the eternal monument, the political statement, the cosmic alignment, the measurement hypothesis, and we will measure them against the stone. Because here is the contradiction that refuses to disappear. If the pyramid were only a tomb, it is overbuilt. If it were only propaganda, it is overcalibrated. If it were only symbolic, it is over-measured. The numbers remain. Base level, approximately 2 centimeters across 230 meters. Alignment, within a fraction of a degree of true north. Corner accuracy, arc minutes. Casing joints, half a millimeter. These are not decorative achievements. They are controlled tolerances. And tolerances imply specification. Specification implies requirement. So what was the requirement? Because it was not gravity, it was not merely survival. It was not simply the stacking of stones into a large, impressive shape. Something drove them to shave bedrock flatter than necessary, to hunt true north with relentless discipline, to refine angles beyond visible need, to polish limestone so tightly that sunlight once struck its surface like a blade. And here we cross the threshold of our inquiry. We are not asking how they built it. We are asking why they refused to build it imperfectly. If it wasn't structural necessity, what was it? If the Great Pyramid were merely a structure resisting gravity, its engineering requirements would be surprisingly forgiving. A pyramid distributes load downward and outward. Every stone presses not only on the block beneath it, but slightly inward toward the center of mass. The geometry itself converts vertical weight into compressive stability, unlike a column which risks buckling, unlike a beam which risks bending. A pyramid settles. It wants to exist. The wider the base, the lower the center of gravity, the steeper the slope, the more force is directed inward. Remove precision from the equation, and the physics remains unchanged. Let us speak plainly. A 6 million-ton stone mass does not require arc-minute orientation to avoid collapse. It does not require sub-centimeter leveling to prevent structural failure. It does not require perfectly squared corners to maintain compressive integrity. Modern civil engineering gives us perspective. Concrete foundations for large commercial buildings, even skyscrapers, are not leveled to millimeter perfection across hundreds of meters. Variations of several centimeters are acceptable, provided load distribution remains within design parameters. Structural engineers calculate tolerances based on stress, settlement, soil behavior, and material strength. In other words, build to what is required, nothing more, because every additional layer of accuracy multiplies cost. Consider the base of the Great Pyramid, leveled to within roughly 2 centimeters across 230 meters, 13 acres. Today, surveyors using laser levels and GPS correction systems would consider that respectable. But here is the essential point. The pyramid would not collapse if that variation were 5 centimeters or 10. It would not even meaningfully shift. The compressive strength of limestone vastly exceeds the stresses imposed by the weight above it. The structure is not delicate. It is a gravity machine. Even if the bedrock had a noticeable slope, say a few inches across the span, the mass would simply settle slightly more on one side. There would be minor internal stress redistribution, but no catastrophic outcome. The King's Chamber granite beams, weighing up to 70 or 80 tons each, sit beneath relieving chambers precisely constructed to divert vertical load away from the chamber ceiling. That is engineering foresight. That is structural necessity. Without those stress-relieving layers, the chamber might have cracked. But the overall alignment of the pyramid to true north has nothing to do with that. The planet does not reward north-facing pyramids with greater stability, and the corners, measured to near-perfect right angles within arc minutes, do not enhance compressive load transfer in any meaningful way. A slightly skewed base would still support the weight. In fact, Glenn Dash's modern survey analysis revealed that the base is not perfectly square, it is very slightly a parallelogram. Length measurement precision appears to exceed angular precision. Even so, the error margins are astonishingly small, on the order of inches across hundreds of feet, which raises a dangerous question. If slight angular imperfections were acceptable, why were they reduced so aggressively? Because here is what structural stability actually requires: adequate foundation-bearing capacity, even distribution of mass, proper internal load relief in chambers, stable material under compression. The Great Pyramid satisfies all of these, but then exceeds them by a margin that suggests intent beyond safety. Now imagine a hypothetical scenario. Suppose Khufu's architects had aligned the pyramid 3 degrees off true north, visibly skewed to modern eyes. Would it fall? No. Suppose the base varied by 10 centimeters in elevation across its footprint. Would the limestone core crumble? No. Suppose the casing joints averaged 5 millimeters instead of half a millimeter. Would erosion suddenly accelerate? No. The structure would still dominate the plateau. It would still last thousands of years. It would still house a sarcophagus in its granite chamber. The physics would remain indifferent. And this is where the contradiction sharpens, because the builders behaved as though the pyramid required something more than physical stability. They shaved bedrock meticulously. Some researchers propose water-filled perimeter trenches used as leveling guides, an elegantly simple technique. Water finds level. Mark the waterline, cut the rock to match. A primitive hydrostatic instrument, yes, but capable of astonishing accuracy. The question is not whether they could do it. The question is why they insisted on doing it to that degree. Engineering textbooks teach optimization. You do not design a bridge to withstand 10 times the maximum possible load unless extraordinary risk demands it. You do not machine components to aerospace tolerances for a farm shed. Over-engineering exists, but it is rare at civilizational scale, because over-engineering is expensive. Precision multiplies labor. Surveyors must check and recheck. Blocks must be recut. Chords must be remeasured. Angles must be corrected. Errors must be traced and compensated. Across 2.3 million blocks, across decades, across a workforce of perhaps 20,000 to 30,000 organized laborers, quarrymen, haulers, stone dressers, copper toolmakers, boatmen navigating Nile canals, administrators recording beer rations and medical treatments. All of this for a monument that, structurally speaking, did not need millimeter refinement to stand. The pyramid shape is forgiving. The engineering decisions were not. Now consider visible asymmetry. Human perception tolerates imperfection easily at monumental scale. A deviation of a few inches across 756 feet would be invisible to the naked eye. Even a slight corner misalignment would not register unless measured. And yet they corrected for it. They hunted right angles. They refined side lengths. They approached true north with obsessive care. Which means this was not about appearance alone. It was not about fooling observers. It was about satisfying a specification. And specifications come from purpose. At this point, if you find yourself unsettled by how little structural necessity explains the pyramid's accuracy, you are not alone. This journey is only beginning, and if you value careful examination over sensationalism, consider subscribing. We are not chasing myths here. We are following tolerances. Because once we accept that gravity does not demand this precision, we must ask what did. Perhaps theology demanded it. Perhaps cosmic alignment demanded it. Perhaps political theater demanded it. But stability does not. The pyramid would still stand, proud and immovable, if its corners wandered slightly and its base tilted modestly. It did not need to be this precise to survive 4,500 years. And that realization is our threshold, because once we admit that structural stability cannot justify the tolerances, we must step beyond physics. So stability cannot explain the precision. Here we can all agree that precision is never free. In modern engineering, every additional decimal place comes at a cost measured in labor hours, material rejection rates, transport complexity, and management overhead. Tighter tolerances demand better tools, more inspections, slower workflows, and exponentially increasing effort. A bridge designed to tolerate a 10 millimeter deviation can be built quickly. Tighten that to 1 millimeter, and the entire logistical architecture must change. Now, place that principle in 2550 BC. The Great Pyramid contains roughly 2.3 million stone blocks. Its total mass approaches 6 million tons. The average block weighs between 2 and 3 tons, but the internal granite beams above the king's chamber reach 40 to 70 tons each. The casing stones, cut from fine Tura limestone, were finished to such precision that surviving joints average around 0.5 millimeter. That is thinner than a modern credit card. Each of those tolerances multiplied across millions of components. To understand the scale of this decision, we must quantify what precision actually demanded. The limestone core blocks were quarried locally on the Giza plateau. Even there, extraction was not trivial. Workers cut channels using copper chisels, dolerite pounders, wooden wedges soaked in water. Blocks were detached, dressed, and transported perhaps a few hundred meters. That alone required organized labor brigades. But the casing stones were different. Tura limestone came from quarries across the Nile, roughly 13 to 17 kilometers away as the crow flies, farther by river transport. These stones were not rough construction fill. They were fine-grained, nearly pure calcite, selected for smoothness and reflective brightness. To achieve joints of approximately 0.5 millimeters, each face had to be measured, squared, remeasured, and polished. Errors could not accumulate. A miscut stone would not average out. It would disrupt the geometry of an entire course. Reject rates rise sharply when tolerances shrink. Even in modern fabrication, tightening tolerance by a factor of 10 can double or triple production cost. In a Bronze Age economy without steel tools, without wheeled cranes, without precision saws, the cost curve steepens dramatically. Then there is granite. The King's Chamber is constructed from red granite quarried at Aswan, roughly 800 kilometers upriver. Individual granite beams above the chamber weigh as much as a fully loaded Boeing 737. Transport required river barges, seasonal timing with the Nile flood, docking infrastructure, unloading ramps, and final placement using levers, sledges, and coordinated teams. Granite is far harder than limestone. Cutting and dressing it demanded immense labor with pounding stones and copper tools. Achieving right angles and flat planes in granite to within tight tolerances is orders of magnitude more difficult than doing so in soft limestone. Now multiply that across at least 43 massive granite beams in the relieving chambers. Precision at this scale is not an incidental byproduct of careful workers. It is systemic. Archaeological evidence suggests a workforce of approximately 20,000 to 30,000 laborers at peak activity. Contrary to older myths, these were not slaves in chains, but organized crews: bakers, brewers, stonecutters, haulers, surveyors, overseers, physicians. Excavations south of the plateau reveal worker villages with planned barracks, bakeries capable of producing thousands of loaves per day, breweries supplying beer rations measured in gallons. Animal bones indicate regular meat consumption. Healed fractures on skeletons reveal medical treatment. This was an industrial project. Administrative papyri discovered at Wadi al-Jarf, notably the Diary of Merer, document limestone transport from Tura to Giza. The text reads like a logistics report. Days counted, crews assigned, deliveries recorded. Bureaucracy was embedded into the process, and bureaucracy hates inefficiency. In any large system, unnecessary precision becomes visible as waste. Extra dressing time per block multiplied by 2.3 million units translates into thousands of additional man-years. Each additional hour of finishing required food, water, shelter, oversight. Let us attempt a simplified model. If a mason spends an additional 15 minutes refining a block to meet a tighter tolerance, and this occurs across even 1 million stones, that is 250,000 additional labor hours. At a 10-hour workday, that becomes 25,000 extra worker days, nearly 70 additional worker years, for a seemingly small refinement. Now imagine the refinement is not 15 minutes but several hours for casing stones. Imagine reworking granite beams that do not meet angular specifications. The cost escalates rapidly. Modern civil engineers design to required tolerances, not aesthetic ideals. A foundation poured to plus or minus 20 millimeters performs as effectively as one poured to plus or minus 2 millimeters for most structural applications. Exceeding requirements consumes budget without increasing performance. Ancient Egypt had finite labor, finite flood seasons, finite food production. The Nile's agricultural cycle governed availability. Workers were mobilized during inundation when fields were submerged. Delays would disrupt farming schedules. Time itself was an economic variable. The pyramid was built in approximately 20 to 25 years during Khufu's reign. To complete 2.3 million blocks in 20 years requires placement of roughly 315 blocks per day, every single day, including quarrying, transport, finishing, and alignment. Introduce tighter tolerances and throughput slows. unless the organization compensates by increasing labor, which they did. Crew names carved into hidden chambers. The Friends of Khufu, the Drunkards of Menkaure, suggest structured rotating teams. The workforce was divided into files, administrative units that could be scaled up or down. Scaling up is costly. And yet the archaeological record shows no sign of corners cut, no evidence of progressive tolerance relaxation as deadlines approached. The geometry remains consistent from base to summit. Even the leveling method implies deliberate excess. The base platform was prepared by cutting trenches into bedrock, possibly filling them with water to establish a horizontal datum. Water leveling can achieve millimeter-scale flatness across long distances, but such accuracy exceeds structural need for a 146-meter stone mound. Survey data reconstructed by modern researchers using linear regression of casing baseline traces shows side lengths differing by less than 20 centimeters over 230 meters. That is a relative deviation of under 0.1%. The corner angles are accurate to roughly 45 arc seconds, about 1 part in 10,000. To achieve this, required repeated measurement cycles, establish baseline, verify with perpendiculars, check diagonals, correct cumulative drift. This is quality control at a level approaching early scientific instrumentation. Engineers do not pay for this unless it serves purpose. Consider the opportunity cost. The same workforce could have constructed additional temples, canals, fortifications. Egypt's Old Kingdom invested extraordinary resources into a single structure whose structural survival did not depend on such micrometric refinement. The pyramid would still stand if its base were uneven by 10 centimeters. It would still stand if its orientation deviated by half a degree. It would still stand if casing joints averaged 5 millimeters instead of 0.5. The additional precision added negligible structural benefit, but it multiplied labor cost, material handling complexity, and scheduling strain. In modern project management, this is called scope creep, unless the scope explicitly demands it. And here lies the crucial distinction. If precision was not accidental and not structurally required, then it must have been specified. Surveyors must have been instructed to achieve near-perfect cardinal alignment. Masons must have been told that joints could not exceed hairline gaps. Inspectors must have rejected blocks outside tolerance, which means the design brief, whatever form it took, valued precision as an end in itself. The Great Pyramid was not merely built, it was calibrated. And calibration, unlike construction, implies reference, a system aligned against something external, but aligned to what, and for what reason, is the question that now begins to take shape. To understand what that means, we must step into the intellectual world of Old Kingdom Egypt, a civilization in which geometry, astronomy, theology, and kingship were not separate domains but facets of a single cosmology. Cardinal alignment is not decorative. It situates a structure within the architecture of the Earth. True north is defined by the planet's rotational axis. To find it requires observation of celestial motion. The Egyptians did not possess magnetic compasses. Magnetic north would not have concerned them even if they had. What they sought was the fixed axis around which the heavens appeared to turn. Above the northern horizon, certain stars never set. They circled the pole endlessly, never dipping below the Earth. These were the imperishable ones, circumpolar stars. Unlike the sun, which dies each evening, or the southern stars that vanish below the horizon, the circumpolar constellations were eternal. In Egyptian theology, eternity was not abstraction, it was geography. The pyramid texts, inscribed a century later inside the pyramids of Unas and Teti, speak of the pharaoh ascending to the sky to join the imperishable stars. O king, you are this great star, the companion of Orion, who traverses the sky with Orion. The deceased ruler does not dissolve into metaphor, he becomes stellar. Thus, orientation was not symbolic in the modern sense. It was literal alignment with the destination of the king's transformed existence. But how was such alignment achieved? The Egyptians possessed instruments of striking simplicity. The merket, often translated as instrument of knowing, consisted of a plumb line attached to a horizontal bar. Used in pairs, along with a sighting tool known as a bay, observers could track the transit of stars across the meridian. One widely supported method involves observing a pair of circumpolar stars when they align vertically, one directly above the other. At the moment of their simultaneous transit across the meridian, a plumb line establishes a true north-south line. Around 2500 BC, candidate star pairs such as Kochab in Ursa Minor and Mizar in Ursa Major would have served this function. Due to axial precession, the slow wobble of Earth's rotational axis over 26,000 years, the identity of the pole star changes across millennia. In Khufu's time, there was no single bright star marking true north. Precision required understanding relative stellar motion. Repeated observations across multiple nights would reduce error. Statistical averaging would refine the line. Once established, that north-south axis could be extended physically on the ground using chords, the ritual known as pedshiz, or stretching the cord. Reliefs from later temples depict the king and the goddess Seshat performing this ceremony together. The king holds a mallet. Seshat, patroness of writing and measurement, assists in stretching the surveyor's rope. The act is not secular, it is cosmic. In Egyptian thought, Ma'at, the principle of truth, balance, and order, governed both morality and physics. The rising of the sun, the flooding of the Nile, the stability of the kingdom, all were expressions of Ma'at. Chaos, or Isfet, threatened from beyond the borders and from beyond the sky. To build in alignment with the cardinal directions was to inscribe Ma'at into stone. Deviation was not merely technical error, it was theological disorder. Yet we must examine this carefully. Ritual does not automatically demand arc-minute accuracy. Many ancient temples across cultures align roughly east-west without millimetric obsession. Even within Egypt, later temples often exhibit looser orientation tolerances. A half-degree deviation would still clearly indicate north. The circumpolar stars would still be reachable in symbolic ascent. So why the extraordinary precision here? One possibility is cumulative ritual significance. The pyramid was not an isolated monument, but the focal point of a vast funerary complex. Valley temple, causeway, mortuary temple, satellite pyramids, boat pits. The entire ensemble was geometrically integrated. Errors at the base would propagate through the complex. Maintaining tight angular control ensured architectural harmony across hundreds of meters. But harmony need not reach arc-minute fidelity. Another factor may involve solar phenomena. The pyramid's faces, when sharply cased, would interact with sunlight dramatically. During equinoxes, the shadow line running down the edges could produce visually precise bifurcations of light and dark. Some researchers propose that tracking equinoctial sunrise or sunset using a gnomon, a vertical rod casting shadow, could produce an accurate east-west line. Modern experiments replicating this method have achieved errors comparable to those measured at Giza. If the equinox was determined by counting approximately 91 days after the summer solstice, an observationally accessible method, then the east-west axis could be fixed with remarkable fidelity. From there, perpendicular construction techniques using rods and isosceles triangle geometry would establish north-south. The mathematics required are not mysterious. They imply organized survey teams capable of repeated measurement and correction. But we return to the central tension. Does the pharaoh's immortal soul require alignment accurate to within 4 arc minutes rather than 40?
Would the imperishable stars reject a king whose pyramid erred by half a degree?
The theological texts do not specify tolerances. Yet Egyptian religion consistently merges cosmic and terrestrial order. The king is not merely ruler of Egypt, he is guarantor of cosmic stability. His coronation renews the world. His death threatens imbalance. His successful ascent reaffirms Ma'at. Perhaps then, the precision was less about celestial navigation and more about demonstrating dominion over measurement itself. To align a 230-meter square to the axis of the planet is to proclaim mastery over Earth and sky simultaneously. The pyramid becomes a fixed interface between rotating heavens and grounded stone. There is also the matter of permanence. Circumpolar stars were imperishable because they never set. A pyramid aligned to their eternal circuit participates in that same endurance. Slight misalignment would not destroy symbolism, but near-perfect alignment dramatizes it. Still, the engineering reality lingers. Such precision required nights of observation, careful marking, correction of cumulative error, perhaps even recalibration over seasons. It required trained astronomer priests whose authority merged technical skill with sacred knowledge. In this phase of our journey, we encounter the mentors of the narrative, the theologians, the star watchers, the surveyors standing in darkness with plumb lines suspended beneath cold northern stars. They teach us that the pyramid is not merely a tomb, it is a cosmogram. But the question remains uncomfortably precise. If alignment served theology, why does its accuracy rival that of early modern observatories? Why does the statistical distribution of corner angles suggest systematic geometric method rather than approximate ritual gesture? When belief meets measurement at this scale, something unusual occurs. And we must now ask whether the cosmos demanded precision, or whether the Egyptians demanded it of themselves. If alignment placed the pyramid within the order of the cosmos, permanence anchored it against time itself. The Egyptians did not build for decades, they built for eternity. The word they used, jet, implied unending duration, a state beyond decay. The pyramid was not intended to last a dynasty, it was intended to outlast history. And so one explanation presents itself with quiet authority. Perhaps the extreme precision was simply overbuilding for permanence. A monument meant to endure forever must be constructed with obsessive care. It is a persuasive argument. The Great Pyramid stands on the Giza Plateau, carved partly into living limestone bedrock. Survey data suggests that much of its foundation was not built up but cut down. The higher areas of rock trimmed, the lower areas possibly filled, creating a level platform within roughly 2 centimeters across a 230-meter square. Some researchers propose the use of water-filled perimeter trenches to establish a horizontal datum, allowing the builders to equalize elevation through hydrostatic leveling. Such techniques would ensure that no corner settled disproportionately. The pyramid's internal architecture also suggests structural foresight. Above the king's chamber lie 5 relieving chambers, stacked granite slabs capped by a peaked limestone roof. These are not burial spaces, they are stress management systems. The enormous weight of masonry above, millions of tons, is diverted around the flat ceiling of the chamber, preventing collapse. This is not symbolic construction, it is engineering. Granite beams spanning the chamber ceiling weigh upwards of 40 tons each. Their placement required calculation of load distribution. The gabled roof above the final chamber redirects compressive forces into the surrounding mass of the pyramid. This is deliberate structural redundancy. One might argue that precision at the base and in the geometry of the structure ensures uniform load paths. If the base were uneven, stress concentrations might develop. Over centuries, differential settlement could produce cracking, distortion, eventual failure. And yet here, we encounter the first fracture in the argument. The pyramid shape itself is inherently stable. It is a compression structure. All forces flow downward and inward. Unlike columns or beams under tension, a pyramid of stacked stone experiences primarily compressive stress, a mode in which limestone excels. Even substantial deviations in alignment would not generate catastrophic shear forces. Modern geotechnical engineers routinely design foundations tolerating settlement of several centimeters without compromising stability. A 2-centimeter leveling accuracy across 230 meters is exceptional, but not structurally required for survival over millennia. Furthermore, the bedrock beneath Giza is geologically stable. The plateau is composed of Eocene limestone with relatively uniform bearing capacity. There is no evidence of major seismic faulting beneath the site during the Old Kingdom. The pyramid does not straddle unstable soils or river sediments prone to liquefaction. In simpler terms, the ground was already adequate. The relieving chambers demonstrate intelligent load management, but such internal reinforcement does not require arc-minute angular precision at the exterior. The stress path from apex to foundation would remain compressive even if orientation deviated by half a degree. Consider durability from another perspective. Material selection. Core blocks are local limestone, adequate but not exceptional. The casing stones were fine Tura limestone, nearly pure calcite, polished smooth. They would have reflected sunlight brilliantly, earning the pyramid its ancient name, Akhet Khufu, the horizon of Khufu. Polishing casing stones to sub-millimeter joints creates a near-sealed exterior surface, reducing water ingress between blocks. In a desert climate with minimal rainfall, such sealing provides marginal benefit. Egypt's aridity already preserves exposed stone. Even rougher joints would have survived with negligible erosion. The casing stones themselves were later stripped in medieval times for reuse in Cairo. Their removal did not destabilize the core structure. The pyramid remained standing, its internal mass unaffected. If permanence were the sole objective, mass alone would suffice. 6 million tons of stone arranged in a broad-based geometry produce staggering inertia against erosion and time. Even weathering at a rate of millimeters per century would require tens of thousands of years to meaningfully diminish its form. Precision did not create the pyramid's longevity, geometry did. One might propose that tighter tolerances reduce internal voids, minimizing micro-movements under thermal expansion. Yet limestone's thermal expansion coefficient is modest, and daily temperature swings in the desert would produce microscopic dimensional changes relative to block size. Slightly larger joints would accommodate expansion without threatening integrity. In modern concrete dams and nuclear containment structures, projects explicitly designed for extreme longevity, tolerances are strict where stress concentration matters: rebar placement, expansion joints, foundation interfaces. But overall, geometric perfection is not pursued beyond necessity. Over-engineering is common when safety factors are uncertain. Ancient builders lacked finite element analysis. Perhaps they erred on the side of caution, refining tolerances to ensure no unknown weakness. But again, the numbers challenge this explanation. The pyramid's base sides differ in length by less than 20 centimeters over 230 meters. Corner angle deviations average around 45 arc seconds. These figures exceed what is required for structural safety by an order of magnitude. A deviation 10 times larger would not compromise compressive stability. The internal passages, descending corridor, ascending passage, grand gallery, maintain straightness and angular consistency across tens of meters. The king's chamber walls are square to within fractions of a degree. Granite surfaces exhibit flatness comparable to modern stone finishing. If the objective was simply to build something that would last forever, the additional labor spent shaving half-millimeter irregularities from casing joints would not meaningfully extend lifespan. Eternity does not demand micrometers, and yet the Egyptians repeatedly articulated the desire for permanence. Texts speak of millions of years. Mortuary temples were called mansions of eternity. Statues were carved in diorite and granite precisely because softer stone decayed. So perhaps precision was a psychological statement, a declaration of defiance against entropy. But even this interpretation wavers under scrutiny. Entropy operates at scales far beyond millimetric geometry. Wind erodes surfaces irrespective of angular perfection. Sand abrades edges. Earthquakes, though rare, introduce stresses unrelated to arc-minute alignment. Longevity emerges from mass, site selection, and material durability, all of which the pyramid already possessed in abundance. Precision did not make it eternal. As we test this explanation, doubt begins to accumulate. If alignment was ritual, permanence was philosophical, and stability was structural, yet none of these require tolerances approaching astronomical instrumentation. Then why were those tolerances pursued so relentlessly? The relieving chambers prove they understood stress. The leveling proves they mastered horizontal reference. The angular accuracy proves systematic geometric methodology. But eternity, as an engineering specification, sets thresholds, not perfection. The pyramid would endure for millennia, even if its base varied by centimeters more. Even if its faces leaned slightly off true north, even if its casing stones met with visible seams. Time does not measure in millimeters. And so we arrive at a discomforting realization in this stage of our inquiry: durability cannot fully justify the precision. The structure is eternal because of its mass and geometry, not because of its arc-minute obedience to cardinal directions. Eternity, it seems, does not require millimeters. So why were they used? Ancient Egypt was a civilization of order, hierarchy, and centralized control. Pharaoh Khufu was the apex of this system, the living embodiment of divine authority. His pyramid was not simply a resting place, it was a monumental declaration of his supremacy, a visual and technical manifesto of what a ruler could accomplish when he commanded not just resources, but obedience. The scale alone was propaganda. Moving 2.3 million blocks weighing 6 million tons, transporting granite from Aswan over 800 kilometers of Nile, and organizing tens of thousands of workers. These feats communicated power in a language everyone understood. Bread and beer rations for the laborers, medical care, housing, and meticulously kept administrative records show that the workforce was both substantial and highly organized. The papyri and inscriptions documenting workers' absences, disputes, and even compensation illustrate a bureaucracy sophisticated enough to manage massive, coordinated efforts. Yet scale alone does not explain the micrometric accuracy at which the pyramid was built. A pyramid could impress through size alone. The base could be roughly level. The sides could meet cardinal directions with reasonable approximation. Even the internal chambers could function with minor deviations. Large-scale monuments, walls, temples, ziggurats are often slightly askew yet convey immense authority. Precision at the level of arc-minutes and millimeters, however, carries a different message. It is no longer mere propaganda. It is control over measurement itself. Here lies the tension. The pyramid scale demonstrates Khufu's dominion over manpower, resources, and logistics. But the calibration, the level base within 2.1 centimeters, the corner angles within a fraction of a degree, the casing joints at half a millimeter, cannot be explained by authority alone. Power can mobilize, organize, and enforce, but it cannot inherently enforce geometry with such accuracy. Calibration requires knowledge, tools, and repeated observation. It requires discipline in measurement that goes beyond the capabilities of mere bureaucracy. Ancient records hint at the administrative effort. A workforce of 20,000 to 30,000 was maintained year-round, with specialized roles for quarrying, transporting, and placing blocks. Supervisors oversaw each segment, ensuring not only quantity but exact placement. Each block was measured, set, and in some cases adjusted to reduce deviation. The sheer labor and coordination involved would have been monumental. Yet one could argue this was not necessary to demonstrate power. A slightly misaligned pyramid would still dwarf any rival monument and still proclaim Khufu's supremacy to the Egyptian populace. This observation invites a critical perspective. Scholars such as Mark Lehner and Glenn Dash emphasize that the precision of the Great Pyramid appears deliberate rather than accidental. Corner angles, base leveling, and orientation reflect a systematic method, not the randomness of skilled labor. Administrative control can enforce task completion, but it does not automatically produce repeatable geometric perfection. There is evidence the Egyptians combined survey triangles, leveling techniques, and cord-stretching ceremonies to refine placement. These procedures suggest a purpose beyond mere construction, an intentional insistence on order. Even the religious dimension cannot be entirely separated from politics. The pharaoh's divine authority was expressed in tangible form. Cosmic alignment of the monument reinforced his status as the guarantor of Ma'at, the principle of truth, balance, and cosmic order. By demonstrating mastery over stone, labor, and sky, Khufu could present himself not merely as ruler, but as intermediary between Earth and cosmos. The alignment of the pyramid with the imperishable circumpolar stars, the meticulous leveling, and the geometric symmetry together broadcast a message of unassailable cosmic legitimacy. Yet power explains scale, not calibration. A monument of comparable size could have been constructed with centimeter-level tolerances or even half-meter deviations and still inspire awe. The difference lies in the absolute precision, the repeated millimetric fidelity over hundreds of meters, maintained across millions of tons of stone. That is beyond what is necessary to impress a population. That is not administrative efficiency. That is mastery of the principle of measurement itself. Political necessity drives construction. Propaganda justifies resources. Control coordinates labor. But none of these factors mandate that the pyramid's sides meet cardinal directions within 0.05 degrees, or that the casing joints be set to 0.5 millimeters. These details reveal a level of intent rarely seen in human history. Engineers today would recognize the sophistication: survey triangles, repeated measurement, correction of cumulative errors, and even statistical techniques to predict deviations. The Egyptians achieved what modern engineers would call a control network for construction, without metal instruments beyond copper tools, ropes, and wooden sighting devices. Consider the cost implications. Every millimeter of tolerance required additional labor, observation, and adjustment. Every block had to be trimmed, placed, and aligned with extraordinary care. Errors propagated quickly in such a system. Small misalignments could compromise subsequent placement. Maintaining the necessary precision demanded continuous oversight, communication, and iteration. That degree of labor expenditure is difficult to justify solely on political grounds. The people would have been impressed by scale alone. Here emerges a subtle distinction. Political purpose explains the choice to build massively and with order. It explains the workforce, the logistics, the brewery on site producing millions of jugs of beer annually to sustain laborers. It explains records, rations, and medical care, but it does not fully explain the insistence on arc-minute alignment and millimetric casing joints. This tension suggests that the political and religious aspects were intertwined but not identical. Power could command obedience. Religion required precision. The pharaoh's authority extended into the cosmos, yet the cosmos had no inherent requirement for millimetric compliance. Somewhere, the ambition of humans met the necessity of divine order. The administrative machine maintained construction, but the astronomical and ritual imperatives dictated refinement. In short, the Great Pyramid operates at two scales, macro and micro. The macro, mass, scale, logistics, communicates political power. The micro, leveling, alignment, joint accuracy, communicates mastery over measurement itself. This duality complicates any easy explanation. One can understand why Khufu needed a massive monument. One cannot fully understand why he needed an almost flawless one. At this juncture, we confront the temptation to accept a simple answer. The pyramid was precise because the pharaoh was powerful. But as we have seen, power alone does not account for the fidelity of geometry. The pyramid's precision hints at a purpose deeper than mere authority. It is here that we must resist the urge to settle for an easy conclusion and continue probing. And as we pause on the plateau, amidst millions of tons of limestone and granite, the lesson becomes clear. Political power explains scale. It explains coordination, resources, and labor. It explains the impossibility of any rival matching the Great Pyramid's presence. But it does not explain calibration. It does not explain millimeters or arc minutes. That, as we shall see, belongs to another realm altogether. The temptation is strong. Accept the obvious explanation and move on. But the Great Pyramid, in its silence, refuses simplicity. Its perfection demands inquiry. The stakes rise, and we step further along our journey, still searching for the force that compels such human obsession with precision. Surveying the Great Pyramid is a lesson in obsession. For centuries, archaeologists have recorded the positions of surviving casing stones, cut lines, and baseline markers, attempting to reconstruct the original form of Khufu's masterpiece. Mark Lehner, director of the Ancient Egypt Research Associates, catalogued 84 points along the pyramid's base, tracing remnants of its lost casing and edges. These points, though fragmented, offer a glimpse of the builder's precision, a precision that defies the expectations of ancient construction. To make sense of incomplete data, engineer Glenn Dash and his team applied linear regression, a statistical method used to predict best-fit lines through imperfect datasets. By estimating the true edges and corners from Lehner's points, they reconstructed the Great Pyramid's original shape with remarkable fidelity. The results were striking. The base, rather than forming a perfect square, is a slight parallelogram. Opposing sides differ by mere centimeters, yet the corners themselves are aligned with arc-minute accuracy. This contrast, slight irregularity in length but near-perfect angular fidelity, reveals a pattern too deliberate to be accidental. Consider this distinction carefully. It is easier to measure length across hundreds of meters than to maintain precise angles. Length can be checked with rods, chains, or ropes. Angle, however, requires observation from multiple points and a repeated method to minimize cumulative error. The Egyptians appear to have prioritized angular control above all else. Corner angles average 90 degrees to within 45 arcseconds, about 0.0125 degrees. Over a 230-meter side, that is extraordinary. Even slight deviations in side length are tolerated, yet the angular geometry is exacting. Why this emphasis on angle? In engineering terms, angle governs orientation, alignment, and symmetry. A building could have minor side length variation without affecting load paths, as we discussed. But the corners define the spatial framework of the structure, controlling orientation in three-dimensional space. In modern metrology, this is recognized as the foundation of measurement integrity. Controlling angles first establishes a reference grid from which other dimensions can be reliably extrapolated. The data suggests that the builders were not merely setting stones, they were establishing a precise geometric reference frame across 230 meters. Repeated surveys, chord-stretching rituals, and sighting techniques likely reinforced these angles, ensuring consistency even as work progressed upward. The parallelogram base may have been an acceptable artifact of practical measurement constraints or terrain irregularities, but the angles, the true skeleton of the pyramid, were sacred, inviolate. Here the concept of measurement intent begins to emerge. These are not casual approximations, they are deliberate, maintained across a massive scale. Metrology, the science of measurement, was not a byproduct of construction. It was an integral objective. Every block, every line, every corner was placed with reference to a carefully maintained coordinate system, one that prioritized angular alignment over mere size. This is an anomaly. Across ancient construction worldwide, scale and alignment tend to drift. Even sophisticated Greek and Roman structures rarely maintain angular accuracy at this level over such distances. Builders are satisfied with square corners within a few degrees, lengths within a meter. Yet Khufu's pyramid achieves an order of magnitude finer fidelity. It hints at a principle more advanced than conventional engineering. The builders were not just erecting a monument, they were orchestrating an exact, repeatable measurement framework across hundreds of meters of stone. And this leads us to a provocative question. If the purpose of these measurements extends beyond stability, beyond scale, beyond even permanence, then what were they really building? Was the pyramid a tomb, first and foremost? Or might it have functioned, simultaneously or even primarily, as an instrument? An instrument not of stone alone, but of alignment, orientation and geometric knowledge, calibrated to the cosmos, to cardinal points, to angles and perhaps even to abstract constants of mathematics. The metrology anomaly, the paradoxical insistence on angular perfection paired with tolerance for minor side-length variation, forces us to reconsider conventional interpretations. It suggests an intelligence, a design philosophy, that valued precise measurement as an end in itself. In modern terms, it is akin to constructing a structure to serve as both a functional building and a laboratory for geometry. This realization casts a new light on earlier questions about alignment, eternity, and political authority. Perhaps these factors motivated the scale, the mass, the coordination, and the symbolic grandeur. But precision, absolute, repeatable, traceable precision, requires an additional rationale. Something more than aesthetics, more than ritual, more than propaganda. Something that transforms the monument from tomb to calibrated machine. For the first time, the possibility emerges that the Great Pyramid might not be fully explained by funerary intent or political display alone. There is a whisper of another layer, a system designed to measure, to calibrate, to record or encode information across space itself. If measurement was a primary objective, then the pyramid is more than a static object. It is a tool. Perhaps it was designed to interact with celestial cycles, to map the horizon, to encode knowledge of the world into its geometry. We have now moved from political and structural explanations to a frontier that touches the edge of human and cosmic intention. The pyramid's angles, measured to arc minutes over hundreds of meters, hint at a consciousness that prioritized exactitude as a principle, a rule, a kind of law in stone. And so the stage is set for a radical reconsideration. What if the Great Pyramid is less tomb, less monument, less statement of power, and more instrument? An instrument whose purpose we have only begun to imagine. Inside the Great Pyramid, the evidence of precision becomes almost tactile. Move beyond the base, beyond the outer casing, and one encounters the internal architecture, a complex system of chambers, passages, and voids that speaks to an unparalleled mastery of stone and geometry. The King's Chamber alone exemplifies this, its walls are lined with massive granite blocks, some weighing upwards of 70 tons, transported from Aswan over 800 kilometers away. Each block fits with such tight tolerances that gaps are often less than a millimeter, a feat remarkable even by modern standards. The chamber's ceiling is composed of 5 enormous horizontal beams, precisely placed to relieve the stress of the superimposed weight of millions of tons of stone above. The stress-relieving chambers above, arranged like a layered ziggurat in stone, create a calculated system to prevent collapse. This is not merely overbuilding, it is evidence of structural foresight married to meticulous measurement. Each layer was positioned to distribute load in a predictable manner, yet the exactness with which the builders placed the stones exceeds what is necessary to maintain stability. Further evidence of purposeful precision comes in the narrow shafts that extend from the King's and Queen's chambers. Originally thought to be ventilation channels, these shafts are aligned with extraordinary accuracy to specific stars, most notably to circumpolar, imperishable stars, and to Orion in the southern sky. Their angles are precise to fractions of a degree, allowing speculation that the builders intended them to serve as astronomical instruments, or at the very least, as conduits aligning the pharaoh's soul with the cosmos. Beyond geometry and astronomy, the pyramid encodes subtle mathematical relationships. The ratio of the perimeter to the height approximates 2 pi, the constant linking a circle to its diameter. The discussion of pi in this context requires careful distinction. It is not clear whether the Egyptians conceived of pi as we understand it, but the correlation between perimeter and height cannot be dismissed. Some researchers propose that the pyramid was designed as a metrological device, encoding Earth-scale measurements or cosmic cycles, using multipliers such as 43,200, which corresponds to the number of seconds in half a day and has been linked to the precession of the equinoxes. Yet here, caution is essential. While these ratios invite speculation, they remain hypotheses rather than confirmed intent. The only indisputable data is the measured alignment, the millimetric placement of blocks, and the geometric regularity of the internal chambers. Ratios, constants, and Earth-scale correlations enter the domain of interpretation, educated, mathematically informed, but speculative nonetheless. It is in this space between measurable fact and philosophical extrapolation that the Great Pyramid's mystery deepens. What cannot be denied is that, internally, the pyramid functions with the precision of a machine. The corridors are straight to within millimeters, the chamber's volumes are exact, the passageways rise and descend with a methodical rigor that implies repeated measurement, adjustment, and verification. Every granite beam, every limestone block, every joint reinforces the impression that the structure was conceived as a calculated system, not a random accumulation of stone. This raises the question, if the pyramid is a machine of stone, what is it measuring? Is it merely a repository for the pharaoh's body and treasures, aligned for ceremonial purposes? Or does its geometry, orientation, and internal regularity encode information about the world itself, the earth, the heavens, or both? The builders may have been engineers, surveyors, and priests simultaneously, blending practical skill with abstract understanding of mathematics, astronomy, and geometry. The idea of a machine need not imply moving parts. Its purpose could be to maintain a precise record of celestial motion, to encode ratios that resonate with the planet, or to serve as a geometric mirror of the cosmos. The internal architecture ensures that whatever it encodes, it does so reliably and with near-perpetual stability. Even millennia later, the angles hold, the corridors remain true. The king's chamber sits perfectly centered under the apex of the pyramid, and so we arrive at a startling possibility. If the Great Pyramid functions as a machine, it is one built of permanence and precision. It operates through geometry, gravity, and alignment. Its controls are millimeters and arc minutes. Its instruments are stones, and its output may be cosmic or symbolic, or both. The question lingers, unspoken yet unavoidable. What exactly was this machine intended to measure, to record, or to preserve? By the time we leave the Great Pyramid and move into the New Kingdom, the pattern of Egyptian construction begins to shift. Temples, mortuary complexes, and even later pyramids rarely approach the precision seen at Giza. Corners deviate by meters, alignments drift, and casing stones are placed with far less care. Even monumental projects like the Red Pyramid at Dahshur, while impressive, do not replicate the millimeter-level accuracy or near-perfect cardinal orientation of Khufu's masterpiece. This raises a compelling question. Why did peak accuracy occur at the very inception of the monumental pyramid age, only to decline thereafter? It is tempting to attribute this to the natural evolution of skill or the availability of resources. Yet the evidence points to something more deliberate. The Great Pyramid appears as a conscious high water mark, a demonstration of what the Egyptians could achieve when intent, resources, and motivation aligned perfectly. Later builders, while competent, may have recognized that such obsessive precision carried immense costs, labor, time, and logistics, without proportionate practical gain. Surveying methods likely played a key role in this targeted achievement. The Egyptians had access to several tools and techniques for measuring angles and distances. The Merket, a sighting instrument, allowed observers to track stars along a vertical plane. By marking shadow positions with plumb lines or simple gnomons, surveyors could establish east-west and north-south baselines. Chord-stretching rituals known as pedjeshis provided repeatable references over long distances. They may have even employed rudimentary leveling systems, such as water-filled trenches or precise sighting across offset rods, to maintain flatness at the foundation level. Yet these techniques, while capable of producing extraordinary accuracy, were labor-intensive. Maintaining angular fidelity over 230 meters requires constant recalibration, repeated verification, and correction for cumulative errors. It is plausible that only under Khufu's reign, with centralized authority, abundant resources, and divine motivation, could such precision be justified and sustained. Later structures, lacking this combination of purpose and support, relaxed tolerances while still achieving monumental scale. In other words, the peak of precision was not an evolutionary outcome, it was a conscious, intentional target. The builders of Giza aimed for a perfection that was culturally, politically, and perhaps cosmologically significant rather than practically necessary. By creating a perfect reference, they encoded a standard of measurement, a principle of exactitude, and a benchmark that would echo across millennia, even if subsequent generations chose not to replicate it. And so, as we examine the history of Egyptian construction, a subtle but profound pattern emerges. Precision is not a constant, it is a choice. Khufu's architects chose to pursue it to an extreme, exceeding functional requirements and embedding within stone a philosophy of measurement, alignment, and intent. The stage is now set for a deeper revelation. If precision was deliberately targeted, if it required resources far beyond necessity, then it served a purpose that transcends architecture alone. The question remains, what was that purpose, and how deeply did it intertwine with knowledge, cosmology, and human ambition? The more one examines the Great Pyramid, the more it begins to resemble not merely a tomb, but a device of measurement, an artifact calibrated to a scale far beyond the human, extending to the Earth itself. Its foundation rests upon a geologically stable plateau, the Giza bedrock, cut and leveled with millimeter precision. This was no accident. A pyramid built on shifting soil would have settled unevenly, its angles distorted, its alignment compromised. The Egyptians, consciously or not, selected their site to function as a fixed frame of reference, a point of constancy in a transient world. Consider the implications. The perimeter and height of the Great Pyramid correspond almost uncannily to ratios that hint at Earth-scale relationships. Some researchers have observed that the pyramid's perimeter multiplied by 43,200, the number of seconds in half a day, approximates the Earth's equatorial circumference. Whether deliberate or coincidental, such correspondences suggest that the builders were thinking not only in meters, but in proportions and measures that extend beyond the visible landscape. This leads to the calibration hypothesis, the Great Pyramid as a geodetic anchor, a stable reference from which other measurements might be derived. Its cardinal alignment, angular exactitude, and level foundation create a coordinate system fixed in time and space. In theory, one could use the pyramid as a datum, a universal point of orientation, to measure distances, angles, or even celestial phenomena with extraordinary precision. The internal chambers reinforce this idea. The king's chamber, the queen's chamber, and the subterranean chamber are arranged with geometric intent. Shafts aligned with circumpolar stars, and the Orion belt suggests that this precision was not merely terrestrial. The pyramid may encode both horizontal and vertical reference planes, functioning as a bridge between earth and sky, as if the builders sought to tether human knowledge to universal constants. In practical terms, such a structure could serve multiple purposes. For surveying, it provides a zero point, a stable baseline from which to measure and map the surrounding landscape. For astronomy, its alignments could mark the rising and setting of key stars or the positions of the solstices and equinoxes. For civilization, it becomes a standard, a monument whose geometry endures beyond rulers, dynasties, or empires. And therein lies the existential dimension. Most civilizations leave behind artifacts, ruins, stories, but rarely a fixed point of measurement. When floods, wars, and time obliterate human structures, what remains is usually chaotic, fragmented, and ambiguous. The Great Pyramid endures not because of scale alone, but because its geometry is absolute. Millimeter tolerances, perfect angles, and enduring alignment allow it to survive as a calibration mark, a cosmic monument to human precision. This is the abyss of comprehension. We are confronted with a civilization capable of erecting structures that could outlast dynasties and dynasties of knowledge, leaving behind not merely memory, but measurable order. The pyramid invites us to consider the fragility of human achievement and the permanence of mathematical truth. Even if empires fall, even if languages vanish, the angles remain, the base remains level, the alignments persist. In stone, civilization encoded a point of reference that may endure for eons. And so we are drawn to the edge of a profound question. If this was intentional, if precision was a metric of survival beyond mortality, what was the Great Pyramid measuring and for whom? Was it a monument to a god, to a king, or to time itself? The Great Pyramid of Khufu has long occupied a paradoxical place in human imagination. For millennia, scholars, explorers, and enthusiasts have argued over its purpose. A tomb for a god-king, a symbol of divine authority, or something more inscrutable. The traditional view holds that it was primarily a funerary monument. Khufu, like other pharaohs, sought eternal life in the afterworld, and his pyramid served as a monumental vessel for his transformation. The chambers, shafts, and sarcophagus were constructed to safeguard his body, store treasures for the next world, and ensure that his ka, or double, could navigate the cosmos. In this interpretation, every stone, every alignment, every labor-intensive measurement was ultimately in service of the divine king and the rituals surrounding his passage into eternity. Yet, when the evidence of precision is considered alongside engineering, metrology, and cosmic alignment, the tomb theory begins to strain under its own weight. A pyramid could function perfectly as a tomb with far less exactitude. Stability requires only that the foundation be roughly level, the angles approximately right, and the mass sufficient to resist erosion and collapse. Internal chambers could be constructed with centimeter or even decimeter tolerances and still fulfill their funerary function. The presence of slightly uneven sides or minor misalignments would not imperil the structure or compromise its role as a royal sepulchre. What then drives the insistence on millimeters and arc minutes? Here enters the measurement hypothesis, a proposition that the Great Pyramid was as much or more a calibrated instrument than a tomb. The geometric precision, the alignment to cardinal points, the internal ratios approximating constants like 2 pi, and the possible encoding of Earth-scale metrics all suggest intentional design for observation and quantification. Its very stones could serve as units in a spatial coordinate system, its angles as reference lines for celestial or terrestrial measurement. Rather than accepting a binary choice, tomb or instrument, it is increasingly plausible that the Great Pyramid served both purposes simultaneously. The duality of function is not unprecedented in human culture. Sacred structures often fuse ritual, symbolism, and utility. In medieval cathedrals, for instance, proportions were carefully calibrated to resonate with musical and astronomical harmonics. The space functioned as both a place of worship and a cosmic instrument. In this light, Khufu's pyramid might be understood as a fusion of theology and geometry. The pharaoh's ascension into the divine afterlife entwined with precise, measurable alignments reflecting cosmic order. This fusion is deeply connected to the Egyptian concept of Ma'at, cosmic balance and truth. Ma'at was not merely moral, it was physical, spatial, and temporal. Aligning a tomb or any structure with the stars and cardinal points was a way of ensuring harmony between human action and universal order. By embedding exactitude into the pyramid's geometry, the builders were not simply satisfying aesthetic or ritualistic needs, they were manifesting Ma'at in stone. In other words, mathematical precision itself became a sacred language. The ratio of perimeter to height approaching 2 pi, for instance, has been interpreted by some researchers as evidence that the Egyptians encoded knowledge of circular constants into a square-based structure. Whether intentional or coincidental, such ratios invite speculation that numbers themselves were vessels of meaning, bridging tangible construction and abstract principle. Likewise, the alignment of shafts with specific stars, the circumpolar imperishables and Orion, suggests an awareness of celestial cycles, linking the pharaoh's eternal journey to the immutable rhythms of the cosmos. In this system, geometry, astronomy, and ritual are inseparable. This perspective reframes precision as an act of worship. Millimeters, arc minutes, and stone placement are no longer mere engineering achievements. They become offerings to the cosmos, tributes to both human skill and divine order. The labor, cost, and logistical complexity that astonish modern engineers, transporting 6 million tons of stone, crafting casing blocks to 0.5 millimeters joints, coordinating thousands of workers, take on new meaning. Each meticulously measured block is simultaneously a practical element of a tomb and a ritualized statement of fidelity to cosmic principles. To evaluate this theory, consider the internal chambers once more. The king's chamber, constructed of granite, is encased within a series of stress-relieving spaces. While these features protect against collapse, a practical concern, their precise arrangement also mirrors the meticulous exterior geometry. The passageways are straight and aligned to fractions of a degree, a level of accuracy that far exceeds what is needed simply to support weight. Here, ritual and measurement converge. The physical act of building in alignment becomes both a safeguard for eternity and a symbolic reflection of order itself. Furthermore, the pyramid's broader orientation reinforces this integration of symbolism and precision. Its base aligns almost perfectly with true north, a direction associated with stability, constancy, and eternal recurrence. Cardinal alignment may have served religious and observational purposes, enabling priests and architects to track celestial events critical for ritual and calendar purposes. Yet the execution required knowledge, observation, and measurement, ensuring that religious symbolism and engineering exactitude were inseparable. If measurement was worship, then the act of building becomes an expression of theology. Precision itself is veneration. Each cord stretched, each rod laid, each stone set is an offering. The monument transcends the individual, Khufu, the workers, even the architects, and engages with concepts larger than life, time, space, cosmos, and the underlying constants that govern both. In this sense, the Great Pyramid is not merely a symbol of power or a tomb of flesh. It is an enduring testament to human comprehension, applied with devotion and ritualized through geometry. This interpretation also contextualizes the anomalies that have puzzled researchers for centuries. The angular exactitude of corners, the tolerance for minor side length deviations, the tight casing joints, the internal ratios, they are not flaws, nor accidental byproducts of construction. They are deliberate choices in the service of dual objectives, a tomb aligned with divine purpose, and a measurement system anchored in the physical and cosmic world. Where traditional theory might see extravagance or over-engineering, the calibration hypothesis and symbolic integration reveal intention and sophistication. By considering the pyramid as both symbol and standard, we also reconcile historical trends. Later Egyptian monuments, less precise and more pragmatic, suggest that Khufu's builders achieved a deliberate peak of precision, not a progressive evolution. The dual function, the sacred and the measurable, required immense resources and a centralized, motivated workforce. Once this peak had been realized, subsequent projects did not replicate the same exacting standards because the functional and symbolic purpose could be fulfilled without surpassing practical limits. The Great Pyramid, in this context, becomes a reference point, an exemplar of the union between cosmology, mathematics, and human ambition. And so, we arrive at a profound notion. Perhaps measurement was not simply a tool or a byproduct, it was itself worship. To measure the Earth, the stars, and the cosmos with such care, and to encode that knowledge in stone for millennia, is an act of devotion. It suggests that for the ancient Egyptians, understanding and order were sacred, that the cosmos could be honored through geometry, and that human precision could echo divine order. The pyramid does not merely commemorate a king, it venerates principles that endure beyond rulers, dynasties, and civilizations. Here, in the interplay of mathematics and ritual, the human and the cosmic, we glimpse a transformation in understanding. The Great Pyramid is not only a tomb, not only a monument to power, not merely an engineering feat. It is a synthesis of knowledge, belief, and measurement, frozen in stone with exacting, almost obsessive precision. This duality challenges us to reconsider what we mean by purpose, by utility, and by reverence. Perhaps the most radical conclusion of all is that measurement, in the hands of Khufu's architects, was indistinguishable from worship. The placement of stones, the orientation of corridors, the alignment of shafts, the calibration of angles, all these acts were simultaneously technical, symbolic, and sacred. In this light, the pyramid is not a passive artifact of human history, it is an active statement of philosophy, theology, and precision, designed to endure, to instruct, and to inspire. The Great Pyramid, in its obsessive accuracy and cosmic alignment, may be understood not only as a tomb for a pharaoh, but as a monumental celebration of order itself. The sacred and the measurable are inseparable. Geometry is devotion, alignment is ritual, millimeters are prayers cast in stone. Perhaps in the end, to measure was to worship. The more one examines the Great Pyramid, the clearer it becomes that the builders of Khufu's era were not merely inspired craftsmen or ritualistic laborers. They were engineers of extraordinary sophistication, operating within a framework of systematic measurement, error correction, and geometric logic. The Old Kingdom Egyptians, often romanticized as mystical or divinely guided, reveal themselves through the evidence of their work as highly competent metrologists, capable of translating abstract mathematical concepts into enduring stone. Consider the foundation of the Great Pyramid. To achieve a base level within 2 centimeters across a footprint of roughly 230 meters, the Egyptians likely employed a combination of innovative surveying techniques. One prominent theory, proposed by Flinders Petrie and later refined through modern studies, suggests that water-filled trenches were used to establish a perfectly horizontal reference plane. By digging shallow channels around the perimeter and filling them with water, surveyors could identify the exact level at multiple points. Any deviation in the water's surface, a natural horizontal plane, would immediately signal an uneven area, allowing them to adjust the bedrock or foundation stones accordingly. This method demonstrates both ingenuity and practical understanding of physics, hydraulics, and geometry. But leveling alone was not sufficient. The alignment of the pyramid with true north required angular precision beyond simple visual estimation. Here, the Egyptians likely employed the merket, an instrument for stellar observation, along with sighting rods and cords. By tracking the circumpolar stars, those imperishable stars that never set, they could determine a fixed point in the night sky to guide alignment. Combined with cord-stretching techniques known as PEDJ-SHEs, they were able to extend precise lines over hundreds of meters, maintaining both straightness and angular fidelity. Evidence of systematic geometry emerges not only in the external footprint, but in the internal layout. Linear regression analysis of corner positions performed in modern surveys by Glenn Dash and colleagues reveals that the Great Pyramid is slightly a parallelogram rather than a perfect square. Yet this subtle deviation suggests not a failure, but a controlled calibration. The Egyptians maintained extraordinary angular precision, prioritizing the orientation of corners over absolute side length. In other words, they understood which parameters were essential for their design's intent and applied error correction methods to preserve them. This shows an advanced understanding of trade-offs in engineering, a level of sophistication rarely attributed to ancient societies. The tools used were simple by today's standards: wooden rods, copper implements, plumb bobs and ropes. But their application was anything but primitive. Rods cut with care provided more stability than cords, which could stretch with tension or humidity. By combining multiple measurement methods and constantly checking their results, the builders minimized cumulative errors, ensuring that the final structure reflected their meticulous planning. Systematic geometry is also evident in the pyramid's vertical elements. The shafts, chambers, and relieving spaces above the king's chamber were carefully positioned to distribute weight and maintain alignment under immense pressure. These features were calculated to millimeter tolerances, demonstrating that the Egyptians were not simply guessing how stone would settle, but applying principles of load distribution, material strength, and spatial planning. The internal layout reflects both functional engineering and symbolic geometry, showing that precision was embedded throughout the project, not just at the visible surface. Viewed in this light, the Old Kingdom builders were far from mystical figures, guided solely by ritual or divine inspiration. They were human engineers, applying observation, measurement, and correction with remarkable consistency. Their work required deep understanding of spatial relationships, empirical problem-solving, and long-term project management. Coordinating thousands of workers, transporting millions of tons of stone, and maintaining alignment across decades would have demanded unprecedented levels of organization and metrological expertise. Even the ceremonial aspects of construction, the PDJs, cord-stretching rituals, the offering of tools to gods, the invocation of Ma'at, can be interpreted as complementary to this engineering mind. Ritual codified procedure, preserved accuracy, and provided standardized protocols for repeated measurement. In other words, ceremonial practice and technical precision were not in conflict. They reinforced each other, embedding measurement into the cultural fabric of labor. The Egyptians' approach to error correction is particularly instructive. Evidence suggests that deviations were continuously monitored and corrected throughout construction. Survey marks, incised lines, and alignment references in both the pyramid's core and foundation indicate iterative checks at multiple stages. This is the hallmark of a disciplined engineering process. Anticipate errors, measure frequently, and adjust systematically. Modern engineers recognize this as best practice. The ancient Egyptians applied it intuitively, without the benefit of modern tools or computational models. When we reframe the Old Kingdom in this way, a new picture emerges. We see a civilization that, while steeped in theology and ritual, achieved technical mastery through methodical measurement. They are no longer merely mystical laborers or artisans. They are early metrologists, architects, and project managers, translating abstract principles into physical reality. The Great Pyramid, then, is as much a monument to the human capacity for systematic thought as it is a tomb for a pharaoh. This perspective transforms our understanding of Khufu's Egypt. Measurement, alignment, and precision were not incidental. They were cultural imperatives, fused with ideology, theology, and societal organization. The Great Pyramid embodies the culmination of these imperatives, a stone machine calibrated to perform both ritual and observational functions, engineered to endure, and meticulously executed by minds that grasped the interplay of geometry, gravity, and cosmic order. As we step back from the technicalities, it becomes apparent that understanding the engineering mind of the Old Kingdom offers a form of rebirth for our interpretation of the pyramids. No longer are we confined to seeing them as inscrutable relics of the distant past. Instead, they emerge as deliberate, measured, and profoundly human achievements, where mathematics and ritual intersected to produce a monument that continues to challenge, inspire, and endure. The Great Pyramid is thus both a product of human intellect and a testament to disciplined observation. It teaches us that precision can be a cultural as well as a technical value, that measurement can be an act of devotion, and that even in the absence of modern instruments, a civilization can achieve mastery over stone, space, and the cosmos. Here, at the confluence of mathematics, engineering, and ideology, we glimpse a civilization transformed through understanding, a rebirth not just of structures but of human potential itself. The Great Pyramid stands not merely as a relic of a long-vanished civilization, but as a monument to a question that has confounded scholars, engineers, and historians for centuries. What problem demanded such extraordinary precision? We have already seen that the tolerances, the base level within 2 centimeters, cardinal alignment within a fraction of a degree, corner angles maintained to arc-minute accuracy, and casing joints almost invisible to the naked eye, far exceed what structural necessity would dictate. A pyramid by its very geometry is stable. Even a misalignment of several centimeters or a deviation of a few degrees would not have caused collapse. Yet the builders labored over every millimeter. Why? One compelling explanation is divine ascension calibration. The ancient Egyptians believed the pharaoh was a god in human form, whose mortal death was only a transition to eternal cosmic existence. His soul, or Ka, needed a carefully prepared pathway to traverse the heavens. The alignment of the Great Pyramid to the cardinal points, and the positioning of the shafts within the king's and queen's chambers toward specific stars, Orion, Sirius, and circumpolar imperishable stars, may have been intended to chart the pharaoh's precise route. This interpretation aligns with Egyptian theology. The concept of Ma'at, or cosmic order, required balance, symmetry, and harmony between earth and sky. Yet here a tension emerges. While symbolic alignment could have been achieved with approximate measurements, the builders demanded accuracy down to arc minutes. Were the Egyptians obsessing over millimeters because they believed the Ka's journey required such exactitude? Could a pharaoh's immortal soul be misaligned by mere centimeters? Some scholars argue that the insistence on precision reflects a worldview in which cosmic law was not merely metaphorical but literal, where deviations in the earthly realm could ripple across the heavens. The pyramid, in this light, was a machine for calibrating the king to the cosmos, an instrument as much as a tomb. Beyond theology, there is the political dimension. The construction of the Great Pyramid required the mobilization of 20,000 to 30,000 skilled laborers, organized with meticulous administrative precision. Daily records inscribed on papyrus noted absences, injuries, and even interpersonal disputes among workers. Laborers were compensated in bread, beer, and grain, and medical care was provided, a remarkable level of social organization for the 3rd millennium BCE. In achieving unprecedented precision on a project of this scale, Khufu's government broadcast its absolute authority. No other ruler could command such resources or coordinate labor with such accuracy. The precision, then, was a form of political propaganda encoded in stone, a tangible, incontrovertible demonstration of centralized power. Yet even here the same paradox arises. Political authority alone cannot explain why tolerances were far stricter than needed for stability or visual impressiveness. Precision was not incidental, it was deliberate and exacting. A third possibility, increasingly discussed among modern scholars, is the idea of the Great Pyramid as an Earth reference monument. Its bedrock was remarkably stable, its base leveled with extraordinary care, and its sides oriented precisely to cardinal points. Some theorists propose that Khufu's pyramid functioned as a geodetic anchor, a fixed point for surveying the Earth itself. If so, the builders were solving a problem of measurement and standardization, creating a terrestrial benchmark that could endure for millennia. In this interpretation, every millimeter and arc-minute of alignment had a purpose, to create a consistent reference for longitude, latitude, or even early forms of map-making. The pyramid could have served as a calibration point for future surveyors, a fixed node in the human understanding of Earth's dimensions. In this scenario, the Great Pyramid becomes not a mere tomb, but an instrument of observation, a physical embodiment of Earth-scale precision. Linked to this is the theory of cosmic encoding or Earth-scale mathematics. Researchers have long noted that the pyramid's ratios, its perimeter to height in particular, approximate 2 pi and other mathematical constants. Some have gone further, suggesting that multiples of 43,200, a number related to the Earth's rotation and precession cycles, appear embedded in the measurements. While such claims are controversial, they point to a possibility. The builders were encoding astronomical and geodetic information into the pyramid itself. The problem being solved may have been the creation of a universal frame of reference, a structure that bridged Earth, sky, and time. Here, mathematics becomes theology, precision becomes ritual, and the pyramid itself is transformed into a machine of knowledge. Yet these hypotheses do not exhaust the possibilities. There is the perspective of legacy and communication to the future. The precision of the Great Pyramid may have been intended as a message to generations thousands of years later, a demonstration that human intelligence, skill, and observation could manipulate the natural world with unparalleled control. Every carefully aligned block, every perfectly level plane speaks across millennia, asking those who observe it to marvel, to measure, and to question. From this point of view, the problem Khufu's engineers were solving was existential: how to leave a signal, a permanent testimony that human understanding could rival the cosmos itself. Millimeters mattered because they ensured that the monument's statement would endure, uncorrupted for thousands of years. Even more speculative theories abound. Some fringe interpretations suggest extraterrestrial assistance, inspired by the sheer improbability of achieving such precision with Bronze Age tools. While no empirical evidence supports alien intervention, the argument persists in popular imagination precisely because the observable precision seems almost impossible. These theories underscore the human difficulty in reconciling such accuracy with our assumptions about ancient capabilities. Whether or not we accept them, they illuminate a core truth. The Great Pyramid challenges every expectation about what humans could achieve, making the question of its purpose urgent and unresolved. Other hypotheses suggest ritual technical fusion, that precision itself was a sacred act. The act of measuring, leveling, and aligning may have been ritualized, a form of devotion as important as the outcome. By executing each measurement with care, the workers themselves participated in a cosmic order, a living ritual encoded in stone. This merges technical problem-solving with spiritual purpose, blurring the line between instrument and temple, geometry and worship. Here, the problem being solved is not just spatial or political, but cultural: how to translate ideology into enduring, measurable reality. We can also examine construction as experimentation, a concept often overlooked. The scale of the Great Pyramid demanded iterative problem-solving, transporting granite from Aswan, precisely shaping limestone, arranging tens of thousands of blocks, and maintaining tolerances across vast distances. Each stage tested material limits, workforce organization, and surveying techniques. Perhaps the pyramid's purpose included an experimental dimension. The problem being solved was discovering the limits of what a society could achieve in engineering, organization, and measurement. The extreme tolerances were part of that experiment, a deliberate challenge to human capability. Finally, we must consider multi-objective intentionality. It is increasingly plausible that the Great Pyramid was designed to solve several problems simultaneously, ensuring divine alignment for the pharaoh, demonstrating absolute political authority, creating an enduring earth-based reference, encoding cosmic mathematics, leaving a lasting message to the future, and ritualizing precision as an act of cultural devotion. This multi-layered intent explains the overkill in precision. Ordinary engineering would not require millimeters. Ordinary propaganda would not demand arc-minute accuracy. But the pyramid achieves both and much more, suggesting a vision that was as ambitious conceptually as it was monumental physically. Each of these interpretations carries its own tension, and none resolves the question entirely. divine calibration, political display, earth measurement, cosmic encoding, legacy, ritual, experimentation. They intersect, overlap, and compete. The Great Pyramid resists simple explanation precisely because it was solving not one, but many intertwined problems, each demanding attention to precision that ordinary structures do not. And this is why modern engineers, architects, and Egyptologists remain astonished. Every tolerance, every carefully aligned block embodies intentionality that is both practical and symbolic, empirical and philosophical. The question intensifies when we consider what we are left with today. Civilization changes, dynasties fall, technologies are forgotten. But the Great Pyramid remains. Its precision, carefully encoded into stone, challenges us across millennia. Was the problem Khufu's builders were solving a practical one, a political one, a spiritual one, or all at once? Was the pyramid a tomb, a machine, a message, or a signal to the stars? Perhaps all of these interpretations hold partial truth, reflecting the sophistication of a civilization that fused mathematics, ideology, and ambition. And yet the central question remains: what problem truly required perfection unnecessary for survival, impossible to justify by politics alone, yet manifest in every stone angle and alignment? Was it human devotion to a pharaoh's journey, to the cosmos, to society itself? Or was it a deliberate act of human mastery, a calibration that mapped the earth, the heavens, and the mind? We stand before the Great Pyramid today, not merely to marvel at its sheer scale, but to confront a profound silence. 2 millennia of human inquiry have passed, and yet the pyramid does not speak in words. No engineering manuals remain. No inscriptions explain the rationale behind the meticulous precision, the nearly invisible casing joints, the alignment to the stars, or the exactitude of the internal chambers. Scholars, engineers, and astronomers can measure, reconstruct, simulate, and theorize, but the builders themselves left no account, no key to decode the intent. The pyramid measures, it observes, it persists, but it does not explain. This absence of direct testimony is both a frustration and an invitation. Without textual evidence, we are forced to interpret from consequence, from outcome, from the structure itself. Every stone, every axis, every minute deviation becomes a clue, a fragmentary language of intent encoded in geometry. Yet this language is alien to us. Modern engineers, even with laser scanning, computer modeling, and 3D reconstruction, can map tolerances to millimeters, estimate construction sequences, and reverse engineer logistics. But understanding why those tolerances mattered remains elusive.
Consider the King's Chamber, massive granite beams transported over hundreds of kilometers from Aswan, raised into position with a precision that challenges belief. The shafts, some mere tens of centimeters wide, angled towards circumpolar stars and Orion with remarkable accuracy. The casing stones, cut and polished to fit with gaps smaller than 0.5 millimeter, once reflected the sun so brilliantly that the Great Pyramid shone like a mirror across the plateau. Each of these achievements demonstrates capability, but capability alone cannot account for intent. The silence of the pyramid forces us to confront a philosophical pivot. When evidence remains but language dies, how do we interpret intention?
In human experience, the destruction of language or the absence of records is usually an insurmountable barrier. We rely on texts, inscriptions, and oral tradition to reconstruct motivation. Without them, we must turn to patterns, to structure, to the consequences of action. And in the Great Pyramid, these consequences are staggering. Precision was maintained where it was not required for stability. Measurements were repeated, recalibrated, and verified in a society lacking metal tools of sufficient hardness to cut granite with ease. Laborers, numbering in the tens of thousands, executed plans that left virtually no margin for error. Every level, every line, every angle speaks of deliberate, obsessive intent. But intent toward what? Some propose that the answer lies in ritual. Perhaps the Great Pyramid was a ceremonial instrument, a stone mandala of cosmic order. Aligning the structure to circumpolar stars could have been a practical necessity for the pharaoh's ascension, mapping the mortal body to celestial coordinates. Yet this explanation raises its own questions. Why arc-minute accuracy? Why base leveling within centimeters over 230 meters? Ritual alone, even sacred ritual, rarely demands such obsessive calibration. Even ceremonial architecture across the ancient world often allows human hands a degree of tolerance that Khufu's builders could not have permitted. Others argue that the pyramid was a machine of measurement, a terrestrial and celestial instrument, a metrological benchmark. Perhaps Khufu and his engineers were defining a standard, creating a fixed point of reference for surveying the Nile Valley, for mapping the stars, or even for tracking Earth's geometry. From this perspective, every millimeter matters. The problem being solved shifts from theology to physics, establishing a frame of reference so precise that it could persist across millennia, providing future civilizations with a reliable scale for both Earth and sky. Yet even the measurement hypothesis is not without tension. The pyramid is massive, imposing, and deliberate. Its precision was costly. Tens of thousands of workers, 2.3 million stone blocks, 6 million tons of material, and years of labor. Was this purely functional, a standard for surveyors yet unborn? Or did the pyramid's symbolic and ritual dimensions demand that these measurements themselves be acts of devotion, the labor of precision, a form of worship? In a culture where geometry, astronomy, and theology were inseparable, perhaps the act of perfecting measurements was itself sacred, an offering in stone. We can look for analogues. Consider modern monuments. Some are designed to impress visually, others to endure, and a few to encode data in subtle ways. The Great Pyramid appears to combine all three. It impresses with scale, endures through millennia, and encodes astronomical and mathematical knowledge in ratios and alignments. Yet the encoding is silent. It does not explain itself. And herein lies a profound existential question. What is knowledge without communication? The pyramid preserves data with incredible fidelity, yet it does not contextualize that data for us. We can read its angles, measure its stones, trace its alignments, and still be left with ambiguity. Its creators understood a language we have yet to fully decode. Some fringe theorists have speculated wildly that the pyramid was designed with knowledge lost to time, perhaps involving technologies or methodologies we no longer understand. Even extraterrestrial theories, though unsupported by empirical evidence, point to a central truth. When confronted with extreme precision, our minds instinctively search for explanations that transcend ordinary understanding. The pyramid's silence amplifies this impulse. The absence of explanatory texts is as significant as the presence of the stone itself. Without a Rosetta Stone of intent, we are left to interpret consequences, and consequences, while revealing skill, reveal little about purpose. There is also the human dimension to consider. The laborers, engineers, and planners who executed this plan did so within a society whose cultural logic is now partially opaque to us. Their worldview fused political power, religious doctrine, cosmic philosophy, and practical engineering in ways we struggle to separate. The pyramid is simultaneously a tomb, a cosmic instrument, a national statement, a legacy to the future, and a ritual object. Its silence forces us to confront the limits of our interpretive frameworks. We may never know whether Khufu's priority was theological, technical, political, or some combination, though the architecture itself suggests that none of these can be excluded. The silence extends to time itself. Over 4,500 years have passed since the pyramid was completed. Civilization has risen and fallen, languages have changed, knowledge has been lost, and yet the Great Pyramid persists. Its edges, alignments, and internal chambers remain precise, an enduring statement of intentionality without explanation. In this sense, the monument challenges a fundamental assumption about human endeavor, that the purpose of action is always documented. Sometimes the purpose is encoded silently, in the execution of skill, in the act of creation itself. The pyramid, in this interpretation, becomes a mirror of human ambition, a record of what can be achieved when knowledge, labor, and intent converge, even if the reasoning behind that convergence is lost. And yet we can make some educated inferences. The presence of stress-relieving chambers above the king's chamber, the careful leveling of the bedrock, and the exact placement of shafts suggest that function mattered, even if the exact function remains speculative. The builders were concerned with durability, with stability, with alignment, and with precision, but they left no written guide. This duality, a structure of incredible fidelity and utter verbal silence, forces us to shift our perspective. Perhaps we have been asking the wrong questions, insisting on explanations in language when the pyramid communicates through measurement itself. Its very geometry is a text, its angles are sentences, its ratios are paragraphs. The silence is not absence. It is an invitation to interpret through observation, deduction, and imagination. We return now to the plateau of Giza, but not as mere observers. We come transformed, having journeyed through centuries of engineering mastery, theological vision, political ambition, and human audacity. The Great Pyramid, once a silent enigma, now speaks more profoundly than ever, not in words, but in its enduring precision. It still aligns north. Its edges still trace the compass with arc-minute accuracy, as though the stars themselves left fingerprints upon its base. The measurements etched into its form, the leveling of its foundation, the near-perfect squaring of its sides, remain unbroken by time, earthquake, or human neglect. For over 4,500 years, civilizations have risen and fallen. Dynasties have crumbled, languages have faded, religions have transformed, and yet the pyramid endures. It does not bend to political whims, nor to the erosion of ideology. It is a monument to knowledge, a testament to human ingenuity encoded in stone. Its existence is not predicated upon belief, upon the adherence of mortals to a particular faith or kingly cult. It requires no ceremony, no priestly intercession. It simply measures, and in measuring, it persists. The king's chamber, the queen's chamber, the subterranean passageways, the stress-relieving voids above, the shafts aimed toward Orion and circumpolar stars. All of this remains intact, an instrument that has survived the collapse of the empire that created it. Granite beams quarried hundreds of kilometers away, transported with sledges and ingenuity, still hold their positions with millimeter-level tolerances. The casing stones, once polished to reflect the sun, guided sunlight across the plateau in a silent demonstration of cosmic geometry. Even the very ratios of perimeter to height hint at knowledge that reaches beyond human lifetimes, approximating 2π with uncanny fidelity. We are left to confront a disquieting reality. This pyramid is less a tomb than a machine. It measures not only the earth and the stars, but the human capacity for precision, for foresight, for the transmission of knowledge across millennia. It encodes standards, aligns reference frames, and preserves data in a form that requires no paper, no ink, no spoken word. In its enduring presence, it communicates what we often forget in the tumult of civilization, that permanence is achieved not merely through belief, ritual, or empire, but through measurement, calibration, and the meticulous alignment of intent with reality. The pyramid's survival and its precision challenges our assumptions about the permanence of human endeavor. Empires rise and fall because they are built on power, ideology, or conquest, yet these foundations crumble. Knowledge, when encoded with rigor, when calibrated to standards that transcend generations, can outlast kings, priests, and scribes. The Great Pyramid does not ask for devotion. It asks only for observation, understanding, and the willingness to measure. Its message is subtle,
almost silent, yet infinitely more durable than monuments of faith or flags of empire.
And here in the shadow of its stone, a haunting thought emerges. Perhaps civilizations do not rise by belief alone. Perhaps they rise by measurement, by the capacity to define their world with precision, to encode their knowledge in a way that survives chaos and entropy. Perhaps the arc of history is not solely driven by ideology, ambition, or war, but by those rare moments when humans choose to impose order upon the cosmos, when they map the stars and the stones with care, when they calibrate their reality to such exacting standards that it can outlive the very cultures that conceived it. The implications ripple outward. Consider our own world, awash in technology, data, and measurement. Satellites map the globe, atomic clocks define seconds, geodetic surveys track continental drift, and quantum experiments probe the very fabric of reality. These modern feats, however, are ephemeral if not recorded, preserved, and calibrated against immutable standards. The Great Pyramid warns us that knowledge without permanence is fragile. Measurement is the true legacy of civilization. It survives belief, survives empire, survives language itself. And yet, even this legacy is contingent. The pyramid stands as a fixed reference in space and time, a benchmark against which the cosmos and the Earth can be measured. But what of us? What of our own constructions, our own cities, our own monuments? Will they endure with the same clarity, the same rigor, when political and cultural tides wash away the foundations upon which they rest? What will remain if our instruments fall silent, if our standards are lost, if the data we take for granted is corrupted or forgotten? We have traced the millimeters of the Great Pyramid, calculated its alignments, considered its rituals, evaluated its costs, and speculated on its purposes. And in doing so, we glimpse a truth far beyond the reign of Khufu or the dynasties of Egypt. Human intention, when coupled with knowledge, precision, and foresight, can transcend mortality.
But the final question lingers, more urgent and existential than any before. When our own reference frames collapse, when language fails, governments crumble, and our digital archives vanish into entropy, what will remain of us? Will our monuments speak of belief, or will they speak of measurement? Will the echoes of our civilization persist, like the Great Pyramid, a silent testament to human ambition, or will they fade into nothing, leaving only fragments and conjecture for those who come after?
The Great Pyramid continues to align north. Its base remains level. Its ratios encode a vision of geometry and order. It outlived empire, religion, and language. And in its persistence, it whispers across millennia that perhaps the true measure of a civilization is not the faith it inspires, but the precision with which it maps the world, both around it and within itself. As the sun dips below the horizon of the Giza plateau, shadows stretch across the stones, tracing the edges and angles with the same fidelity they have maintained for 4,500 years. We step back, humbled by the scale, the intelligence, and the quiet audacity of its builders. We realize, finally, that the story of the Great Pyramid is not only about stones, or kings, or stars. It is about humanity's attempt to impose order on the cosmos, to leave a mark that speaks across the ages, long after voices are gone and empires have fallen. And in that realization, the haunting question returns, sharper than ever. When our own reference frames collapse, when the instruments we trust and the monuments we build can no longer anchor reality, what, if anything, will remain of us? Perhaps belief alone is insufficient. Perhaps it is in the act of measurement, in the discipline of precision, in the fidelity of construction and observation that civilization finds its true immortality. The Great Pyramid still stands, silent but articulate, a machine of stone that outlives the living, and a mirror to the ambitions of every human age. It does not require our worship. It does not demand our understanding, but it does demand that we measure, reflect, and ask. In the span of time yet to come, Will we too leave something that endures, or will the silence of our intent render all that we build meaningless? And with that question hanging over the Giza plateau, we leave the pyramid not as passive observers, but as witnesses to a truth both stark and awe-inspiring. Civilization at its highest may not be defined by belief or power, but by the courage and rigor to measure, to impose order, record knowledge, and calibrate our world with care that outlasts us all. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.